Okay, everybody, welcome to week 4. I'm calling this lecture 7, and this week we were, what's that?
We have a
full class. Yeah, we got two students here in class today, so we can do whatever we want. No, what I want to do is a couple things. I just want to first make you aware of the fact that I did go ahead and push out a quiz 3. And let me show you, there's only 2 questions on it right now, and I'm just going to leave it simple. But I wanted to remind you that this is the required textbook for the course. And I just put just a really simple question from chapter 1 in there. So it's just to make sure that you're reading and paying attention. And then I put another question there, a quantitative question that is comparable to the embodied energy lecture that I gave last week. So let me just go back into the course, show you where that is. It's super simple. Week 1, week 2. So there it is. Oh, and I just need to edit it so it doesn't say quiz 2. That one talking. So this is quiz 3, and it's just one little thing on embodied energy and another thing on the reading, or the book. And just so we're all up to speed on how to do that problem, I'm going to give you a little sneak peek. Into what we're looking at. So I'll just... And since we're talking about landfills this week, I will take a shot at, well, a couple things. One is looking at dollars per pound of landfill, basically. So let's go back to the question of how many dollars we spend per year on waste going into the landfill. So this is just the University of Montana. When we did the interview, and a lot of people posted numbers from that interview with Eddie, we came up with $400,000 per year. And what I'd like to do is figure out how many pounds we think we put into the landfill from the university. So let's go back to our...
Well, don't you have to know how much it costs? I mean, each...
How much what costs?
I mean, like each dumpster is going to cost?
Oh, well... we would have to know how much each dumpster would cost, but we don't in this case because we know what the total bill is. This is all of the dumpsters for the entire university. And this actually includes penalties as well. When something's not next to the dumpster, there's a surcharge depending on how many people are involved in chucking something in the back of the truck. So $400,000 a year. I'm just going to estimate 15,000 people at the university. And in Montana, I think the waste stream was on the order of 7 pounds per person per day. I'm going to guess that at the U, so we're splitting our waste streams between the university and our residences. So let's put that in there. So 15,000 people. I'm going to start with 7 pounds per day, and then I'm going to throw in, let's just say 0.5. This is work versus home. Hey, what's going on, Jason? Well, so the question is, do you throw everything away at the university, or do you throw everything away at home? And the answer to both is no. I'm going to say you probably throw half of your stuff away. Well, if you're living in the dorms, then the answer is probably everything, right? Is that true, Priscilla? Okay. So maybe the number's a little bit higher than that, but we could play with that number.
But why do we have to put that in there, though? Because this is already in the dumpster.
Well, because let's say you dispose of 7 pounds of waste per day, 3.5 of it goes in your dumpster at home, and 3.5 of it goes in your dumpster, in the university's dumpster, and contributes to that bill. Question?
Okay.
It's just an estimate. It's
why you're putting that in there. If we're looking at the university itself, and including student housing, that there's just that part right there isn't, the 400,000 isn't about the recycling, that's just about the landfill.
Yeah, and what I'm working on right now is trying to have an estimate as to how much matter goes into the landfill. I want to get a pounds per year, and then I want to get a dollars per pound.
Okay, so wouldn't that all be though? There's nothing that goes into the landfill that goes into the dumpsters, that goes to the recycling center.
Yeah.
So why would you put in the 0.5 of what would go from home to work? I just don't understand all that.
Well, so if, it's a good question. So if I didn't put any of my own waste, if I didn't subscribe to a curbside service, let's just say, and I threw everything away at the university, what would this number be instead of 0.5? No, if I personally was an average person with a 7 pound per day waste stream, and I took it all to the university, and so did everybody else, what would that number be? It would be 1. It would be 1, because it was
I just don't see the relevance of putting that in right now to find out how much a pound per day will cost. Because that's just like, you'll never get an answer to that. I mean, you're just like sticking that into.
Well, the bottom would be if the university didn't have a landfill service and everybody took their garbage home, what would that number be? It'd be 0. So the number is, and again, I think we even had this conversation last week. There's as many numbers as you want between 1 and 0, and I'm picking one that's convenient. It's 0.5. So this is an educated guess, and we can put a bound on it too. When we finish this little problem, I could very easily double the number, just like we did with the propane torches. We got sort of dollars per gram of gold, if I remember correctly. So again, this 0.5, yeah, you're right. It does complicate things, but it gives you a little knob to turn or to tune, because what I would like to do ultimately is turn this little knob all the way down to 0. We don't have a landfill bill at all for the university. That's where we'd like to be. Does that make sense now? Is that why you see why I'm putting the little knob there?
Yeah, okay.
This is as much a design problem as it's an engineering design problem as much as it's just sort of an accounting problem. I'm sort of bridging the gap between those two problems. Okay, so 0.5 per day, and then I'm going to multiply, so 365 days per year equals, all right, so let's just do that, a little bit of math, 15,000 times 7 times 0.5 times 365 equals 20 million pounds. Is that right? Yeah, 20 million pounds. Gosh, it seems like a lot. 20 million pounds. LBS, And I'll divide that by 2,000 to get tons, so divided by 2, just for fun, 2,000 equals, so I'll call that, somehow, 9,000 tons seems like less. You know, 9,000 tons is basically 9,000 truckloads, you know, pickup truckloads. Yeah. We can just call that 10,000 tons.
I like how you round up.
Oh, well, you know, the only reason one justification for rounding it is that this number was very vague. Okay, so $400,000 per year, 20,000 pounds. Let's look at the dollars per pound now. So let's just run that one more time. So 400,000 divided by 20 million. Okay, so we're running at 2 cents a pound to 2 cents a pound liability. That's the cost, right? So this gives us 0.02 per LB. Okay, so that's what it costs just to move whatever, you know, and what I'd now like to do is see if we can turn that liability into an asset. So let's use what we figured out last week with the embodied energy and the energy density. Well, more energy density. How much energy is there, and see what energetic value that waste might have. So do a little research, and this will help you for the quiz problem that I just posted too. Pretty simple.
Why didn't you use the $400,000 per year?
$400,000. Did I make an error? Let me pull up Microsoft Excel. So we're looking at so cost per year. This is going to be in dollars, and this is going to be mass per year. This is going to be in pounds.
Did you know even if you put in that 0.5 and you took it out and just did the math, it comes out the same, 2 cents?
What's that? What's that?
Well, if you took out the 0.5 and just did the, 15 times the 7 times 365, and you divide it by the 400,000, it still comes out to be 2 cents.
We'll do it both. We'll redo it in Excel. I'll double check. Sometimes you can make an error there. So cost per year, we know, is $400,000. So that's known, and I'll format that. Control 1. Currency, here we go, 0 decimals. Okay. And yeah, just in the spirit of completeness, let's just go, this is going to be people, 15,000. This is going to be mass per person per day, and we've got that at 7. This is going to be in LBS, pounds. Fine, okay. And then we're going to do fraction at the U, and we'll put in 0.5 for now. And then days per year. 365. Okay, so we've got 15,000 people, so more, well, first let's figure out what we're calculating. This is going to be mass per year in LBS, in pounds. Okay, so this equals, so more people is going to make more garbage, times more garbage per person is going to make more garbage, times a greater fraction at the university, times the number of days per year. That's not going to change. There we go. So control 1, number, 0, 0, bing, bing. So looks like I did the math right. If I come in here now and say, oh, well, it looks like I've underestimated, it's probably closer to 0.7, you can see right away that that number increases, and I can take it all the way up to 1, and there you go. We got 38 million pounds instead of the 19. So I'll go back and put that to 0.5. Mass per year. So what I'll do in this little box, just say that equals that number. That's what we were after in the first place. Insert a new cell here, and this is going to be cost, and now we're going to put it in dollars per pound. So equals dollars divided by pounds. Put a couple more significant digits on that. So 2 cents per pound, 2.1 cents per pound. Is that clear? I don't think I made any errors, right? Okay, good. So it's good to redo that. Oh, and in fact, let me take this, and I'll just label it. Montana garbage. Hey, I was talking about you. Just kidding. Mr. Montana. This, and I'll call this incinerator. I'll finish this problem up, and then we'll take a break. Okay. Okay. So what we just finished looking at was how many what the liability cost is. So we're looking at solid waste as a liability. It's a 2 cent per pound liability, right? So you hand your 1 pound item of refuse to the custodian. Well, I don't know. For him it might be a penny a pound, and then another penny. Well, it's weird to think how the whole stream works, because we're actually paying for it in a couple ways, right? We were paying for. I didn't factor that in either, because we pay our facilities on top of this, because they're actually handling it before Republic touches it. So it's actually going to be more than this. But this is just the Republic cost. This is what it costs our facilities, or our facilities guys and gals to hand it off to Republic. So we actually take a hit before that. 2 cents per pound. Okay, so what I want to do is flip those numbers and see if we can't turn that liability into an asset, right? We've seen it with other materials, and let's see what that would be. So I did a little research, and let me get into this. Back into NRGY 270. And I just came across this paper on municipal solid waste. So methodology for allocating municipal solid waste to biogenic and non-biogenic energy. So that's basically your compost there, and this would be more incineration or what have you. May 2007, Office of Coal, Nuclear, Electric, and Alternate Fuels. I like that rather than alternative. I'm actually going to be in DC next month, and I've got meetings with some of the fossil fuel deputy secretaries discussing some technologies that I've been working on in this field. So this is a little old, but I think once we take a look at this table, this is what I'm looking for right here. It says Table 1, Municipal Solid Waste Heat Content, and biogenic, non-biogenic shares, et cetera, et cetera. Let's take a look down there. Table 1. Okay. So there's the heat content. What could we use heat for? Keep a building warm would be one, and that's pretty obvious. Or cooking would be another one.
Generating steam.
If you get it hot enough, you can make steam. If you make steam, you can make electricity. Cleaning, a lot of stuff. But there's the heat content. So we'll now look at that number, right? Because when you go to buy when you pay your heat bill, I mean, you're paying for methane basically to be pumped to your house. And this, well, we'll dig into it. Here's what they're looking at right here. Of that heat content, 2/3 of it is biogenic. This is just, methane coming off the stack that could be used. The rest of it, we can dig in, I'm assuming is just for direct combustion. So, but let's just take that 10 BTUs per ton, and I want to see what, how we might turn that energy into an asset rather than a liability, turn that mass into an asset. So let's just take that 10 million BTUs per ton. So let's go back in here. Let's look at this incinerator. So on this half, we basically have just going to the landfill, no energy recovery. On this half, we'll have full energy recovery. So I started out with waste in kilograms per day, and we can actually, so let's do that. First, let's just start out with pounds per day waste. And we're going to put this in LB per day. So if we start, well, let's actually go back here. Mass per day, days per year. Let's stick in one other little cell here. This is going to be mass per day in LBS. And basically that just equals number of people times total garbage times that one number, ding, 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 ding. Okay, so 52,000 pounds per day. Let's just get fancy here and say this equals this number. That worked. Okay. Now let's go ahead and convert. Actually, I'm going to take this whole thing right here. Paste it over here. Equals. Okay, there we go. So we'll take the. Is that large enough to see? Sorry, the screen's kind of bleached out again, but it's large enough. Okay, so we'll take the pounds and convert them to kilograms. Excuse me. Equals this divided by 2.2. Control 1. Always nice to have your numbers in the same format, so you can sort of just inspect them and say, okay, I can believe that is correct. Now, I want to look at this like a power flow problem. So I've converted kilograms per day to kilograms per second. So hopefully up there in the formula bar, you can see that I've just got the mass flow rate per day, and I've just divided that by 24, then 60, then 60. So the university is creating mass at a rate of 1/4 kilogram per second. You can sort of imagine what that stream would look like. You can even think of it as almost like a pellet stove, right? Just sort of feeding into, and in fact, that's exactly what we're doing. We're feeding it into a waste-to-energy recovery unit. Maybe it's incinerator, maybe it's a pyrolysis unit, what have you. Now, the next trick is to come into the paper, and we can see that municipal solid waste has a heat content of 10 million BTUs per ton. So what I've done down here, I've just typed that number in, and this is from MSW DOE 2007. That's where that reference comes from. There we go. Now, I'm going to convert from BTUs to joules. There are 1,055 joules in a BTU. I have then converted that to megajoules per ton. So right up here I've got 1,000,000 BTUs. That's the conventional abbreviation for million. That's MMBTUs. So I've got this now at megajoules per ton. That's multiplying 1,000,000 BTUs per ton. I've got 1055 joules per BTU. So if I want to know megajoules, I can just use the fact that I've already got 1,000,000 BTUs built in. Is that making sense? It might be a little confusing keeping track of the units. Is that clear enough why I did it the way I did? And then, so that's megajoules per ton, or kilojoule or megajoules per kilogram. So I've just divided that by 1,000 to get from tons to kilograms. And again, this is order of magnitude accurate. We don't have to get too crazy with it. So from there, I can simply put in that, I can just put in 10. That more or less the heat capacity, I'm just calling that C sub P, it's different from the thermal capacity that we used to melt gold last time, but I'm just using that as a heat content. Energy per kilogram at 10. You can change that to kilojoules per kilogram. So obviously there are 1,000 times as many kilojoules as there are megajoules. And then finally, if I have the mass flow rate in kilograms per second, and then I multiply that by the number of kilojoules per kilogram, that immediately turns into kilowatts. So the university could be running a 2.7 megawatt heat generator with the waste. Does that make sense? Okay, I'm going to pause there because we've got about a half hour, take a break, and be right back. There will be a problem a lot like this on that quiz 3. So, and most of it's just kind of keeping track of units. So if you have a question on that, we can revisit it after the break. I also want to show you something that Sean Doty posted from his volunteering at the Hazardous Waste Days. So we'll look at that together too. Okay, quick break, I'll be right back.